Hello, everyone. I'm Jim Benson. I lead strategic alliances and marketing for the Intelligent Cities business inside of Current by GE. I want to welcome everyone to today's webinar, Building Blocks for an Extensible Smart City. Before we get started, I'd like to go over a few items so you know how to participate in today's event. Our distinguished speakers will review the materials they prepared, and then we'll save all the questions for the Q&A session at the end of the webinar. Please submit any questions you have at any time during the webinar. Simply text your questions to the presenters by typing into the Q&A panel of the control panel. We also, throughout the presentation, will have a few polling questions. We encourage you to answer those and share with us some of your thoughts on what you guys are doing in your cities and utilities today. And with that, I'm going to turn it over to our two speakers today, Austin Ashe from Current by GE and Sameer Sharma from Intel. Austin, please introduce yourself and then kick it over to Sameer to do the same.
Good morning, good afternoon, good evening, everyone. Thank you so much for joining us today. I'm Austin Ashe. I am the General Manager for Intelligent Cities at Current by GE. Looking forward to speaking with you all. Sameer?
Thank you, Austin. Hi, everyone. This is Sameer Sharma. I manage a global team that looks at smart cities and intelligent transportation solutions for Intel, working with our partners. I want to turn it back to Austin to start with some of the content.
Yeah, thank you, Austin. Please take it away.
Thanks, Jim. To start today's discussion off, what I wanted to do is set the table for what the building blocks of a smart city are. The building blocks of a smart city are revolving and evolving around data. When we think about how cities are adapting to increased population growth, to increasing demands from citizens for new services, what cities are ultimately trying to accomplish is to become a more workable, playable, and livable city, not just for citizens, but for visitors, for students, even for local entrepreneurs. Everyone that lives in the local economy is wanting a more vibrant city and a more vibrant experience. And when it comes to data in particular, cities use data every day to help make decisions. They use data for planning. They use data to help citizens understand things happening in the city. And what is more critical now than ever is to actually get their hands on more ubiquitous data. What exists today are data sets from certain populations or certain timelines or timeframes or locations, but it is not a comprehensive or ubiquitous amount of data that actually strings together. If that were to come together and happen, cities would be a lot more efficient, a lot more effective, and a lot more knowledgeable about how their city wakes up every morning, goes to bed every night, and how things change day to day, hour by hour, even minute by minute. What cities are also trying to do is open the data up. You'll see many cities like San Diego and Portland and Chicago have open data portals where they're trying to get as much of the data as they possibly can out into the open and introduce a new level of transparency into the community and actually invite citizens in a more intimate way to help them think about problems and solving for some of the challenges that exist in each city. But to do that, the city has to be actionable as well. So the data that's coming in has to be able to be translated into a meaningful outcome. The other thing that's important for cities is that these building blocks that cities are looking for are owned by them. They are in the best position to create policies for these data, figure out what data needs to be open, what data is open but redacted, what data needs to be approved for use, etc. And when it comes to the various types of data sets that are out there, just the sheer volume and veracity of it, it's really important that the ownership of that falls within control of the cities, because they're in the best position to know how their local citizens and their population will access the data. The next thing that's really important is this data needs to be cross-departmental, or more horizontal, if you will, in nature. One data set that comes into one department is very useful, but it's even more useful if all the departments in the city get access to that same data and can utilize it for their own benefit. That's very, very challenging to accomplish all of these things today in a very elegant, cost-effective, and scalable method. But even more importantly than that, what's needed from these particular buckets of data is that it become real-time. What we're learning is that cities really need real-time data to actually have a more instantaneous and positive effect on the citizens and in their own operations. So how do you find this data? How do you extract it? How do you deliver it in a way that meets all of these needs in a way that helps a government or a city shape their solution set? When we think about it, we think about the streets and the sidewalks within the city as sort of the nervous system within a city. And what if we could put our finger on the pulse of that nervous system? Would that help give us enough information about how that system is working day in, day out, minute by minute? And when we think about the nervous system, unlike our bodies, right, even though we have a nervous system where nerves are flowing, cities have a nervous system where there's traffic, where there's pedestrians moving around, where cars are parking, where there's public safety concerns, where the environment is changing, sometimes minute by minute, hour by hour, and sometimes in microclimates. We also know that there's bicyclists moving around everywhere, and cities are trying to promote more and more usage of bicycles and public transportation. There's, things like shopping carts that show up, or even stray dogs or animals, folks in wheelchairs, or even moms rolling strollers. There is just so much happening that where the citizens are utilizing the arteries of the city. And what's really, really critical is that the real-time data that we are delivering in a ubiquitous manner across all these departments actually address these data sets that make up the movement of the city. And so by transforming your digital infrastructure, by transforming infrastructure into digital infrastructure, you can bring about change in a significant way that is very, 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 very new and apparent and happening today, day to day. So what I wanted to do is take a quick pause, and I've been asked to ask you all a question. So if you could go into the system and answer, we'll give you about a minute to ask this. But when it comes to the topic of real-time data and sensors, the question is, are you currently obtaining any real-time data with the sensors and or beacons if you use this, that type of system? And if so, what type of real-time data are you obtaining? Again, we'll give you about a minute to think about this. There's a few options there around pedestrian, traffic, parking, things like gunshot detection, pedestrian flow, air quality, others, or you can just let us know that you're not collecting real-time data today. Okay, thank you all very much for answering that question. We will consolidate those and report those back out later on. But what I really want to get to now is to talk about how platforms are evolving in both the consumer and in the city space, because when we talk about extracting real-time data and repurposing infrastructure into digital infrastructure, there are a number of paths of doing it. And one of the sources of inspiration that Intel and GE got when we started down this path was reflecting back on the iPhone when it was unveiled. And what you'll recall, if you've ever seen the unveiling of the phone from Steve Jobs back in 2007, he showed us that Apple was coming out with a new phone and a new PDA device and a new MP3 iPod type device and a camera and a gaming console and a GPS device, right, and a television or video viewing device and something that had a flashlight. And what was revealed was all of those things that we were living with individually day to day were being consolidated into one elegant device that we all know and love as the iPhone. Or if you're an Android user, right, there's a whole bunch of smartphones out there on the market from various vendors. But what ultimately this proved is that we can consolidate all of these devices because of technology into one platform, and then we can virtualize the solutions that we want through apps, right, through software. And just like the iPhone transformed the way people think about devices and getting data and using data and solving problems, at least at a personal consumer level, we see the exact same trend happening within cities. So today, for example, cities use things like induction loops to help them trigger traffic light signaling. They also use things like smart parking pucks that sit in the asphalt and are battery powered and help detect whether a car is present or not in a parking space. They use acoustical sensors for gunshot detection and other acoustical type measurements in the city. They use CCTV cameras for surveillance and other public safety type measures. They use weather stations where they place these strategically around the city to get information about temperature and humidity and pressure. And when you think about all of those individual devices, the question becomes, how do you scale all that? And even bigger, what if you could consolidate all of those devices and then some into one elegant device that could fit on a streetlight and actually serve all of those functions that those independent sensors do, but now it can do it virtually through an application store. That is the platform that Current at GE and Intel have built and developed together. Think about it as a smartphone that goes on a pole. And so what does this smartphone device actually kind of do? Well, not unlike a consumer smartphone, which has probably 12 to 14 sensors in it when you add up the touch screen and the GPS and the microphone and all those kinds of things. The Intel-powered solution with Current has over 30 sensor capabilities. Not only that, but it can connect via Wi-Fi, it can connect via Bluetooth, it can connect via cellular, and all of those sensor devices that are extracting incredibly powerful, ubiquitous, real-time, actionable, city-owned data, it's bringing that data up to the cloud where our APIs are then opened up through the open platform to the development community. And just like on your smartphone device that you have in your hand right now, where you can go to the App Store and download apps, we are enabling an ecosystem of application developers that are building apps that can help virtualize any solution set for a city anywhere in the world. When we think about the data that's required, we already talked about the traffic and the parking and the pedestrian and all the other aspects of things that we can do with this. But it's really important to think about who can get access to this data, right? Analytics departments in cities now have 24/7 real-time ubiquitous data. Application developers that do gunshot detection or parking guidance or traffic management now have access to the data. Even folks within the city that you may not normally think of as an application developer. What about folks like entrepreneurs and incubators in a city that are looking at the next startup idea? what if they had access to this data and could come up with a very clever use case with the data? What about high school students and college students? Cities are looking for ways at educating our up-and-coming future about coding and about apps and the digital world. And it's very interesting to think about the fact that all this data that's open and out there and available via API could actually be leveraged by students to build the apps that they want to see and live and work with every day. And so this platform end-to-end is what Current and Intel have built together. And for those of you that don't know, we actually partner with AT&T in the US and Mexico and with Nokia in Canada to make this solution both communicate viably on a robust, secure network, as well as from a commercial perspective. Now, when it comes to the technology that's inside this sensor, it's really important to think about all the other consumer-type devices that are coming out that have machine learning and edge computing technologies in them. So let's just think about a couple examples that we're all familiar with today. Smartphones that we've been talking about for the past few minutes have a face unlock feature, right, where it learns what your face looks like and your face alone. And by looking at the camera, you can then unlock your device. Even some tablets have this today. Amazon Alexa, right, and Echo. Those are devices that use machine learning. They take your audio input and translate it into an action, right? Hey, Alexa, turn on the lights. Hey, Alexa, play my favorite song, right? And the machine actually gets programmed to learn how to detect your voice and extract the meaning for what you're trying to get out of it, and does that for you. Even Nest, Google Nest thermostats have machine learning algorithms that predict when you're going to be home and what type of energy consumption you like in your home, whether you're more conservative or like more air conditioning, more heating. We've even seen this in play with things like AlphaZero, who is a chess system that Google built, and within like 4 hours, it beat Deep Blue. 4 hours of training on chess, it beat one of the most sophisticated chess systems ever known to man. And it taught itself that through a machine learning algorithm. Even shopping ads, right? Something as basic as going online and shopping. You search for something one day, and the next day it reminds you that you searched for that, right? And it's constantly adding pattern recognition to your feeds. And even smart replies on emails, right? It's on your phone, on your email, you're starting to get suggestions on how to reply to messages. So all of these machines are kind of helping doing the thinking for us, right? And very similarly, what our technology does that Intel powers for us is it does computer vision analytics on the edge. So all those amazing data sets that we talked about, the traffic and the shopping carts, that is all made possible by computer vision analytics. And so what you're seeing on the screen right now is an example of what computer vision is. It's the science or the art, Intel might argue, of translating pixels into meaningful pieces of data that we can then extract and provide to the cloud. And so you've seen a couple examples here about parking, about traffic, about pedestrians that are playing on your screen. And again, what we're trying to show you here is the variety of data sets that we can extract. And ultimately, because this technology is extensible, we can update these sensors over the air with any application that you want to run on the edge, whether it be the shopping cart or animal detection or other. And that's what makes it so powerful, is any and all data sets that you're interested in, you can choose when to update them, how to update them, and then who you give access to. And similarly, like the Alexa example that I use on the consumer side, we have an acoustical sensor inside the node that helps us hear things and alert officials to things like gunshot detections or screeching tires, or maybe you want to look at the other end of the spectrum and know where all the quiet areas are in a city. There's a lot of fantastic use cases that can be utilized from an acoustics perspective. And so that lays the groundwork for what it is that we are doing together for cities, but I want to turn it to Sameer to take us a little bit more in depth on this great edge computing technology. Sameer?
Thank you, Austin. And as you were talking through the slides, I was reflecting back on the joint journey and the partnership that we've had together to basically conceptualize, develop, launch, and now scale this product. And it's been a fascinating journey. We've learned a lot, and I'm pretty proud of the impact that we've already had in terms of initial deployments, but I'm even more excited about where we're going with this. So folks, while Austin was going through the content, I actually looked at the profile of the audience who are listening into this webinar. And I'm very glad to see that we have everyone from cities, regulatory bodies, utilities, technology companies, consulting companies, system integrators, and many others on the call. And this is exactly the kind of thriving ecosystem we need to pull these solutions together. Because cities are hard, cities are complex, but we can get there assuming we work together. I'm going to complement what Austin has shared about the product with a couple of perspectives. The first one is what exactly is happening at the underlying technology level, at the platform level, that's driving all these things to become real, all these use cases to become both technically feasible and then they also now make sense from an economics perspective. The second thing I'm going to try and overlay is the sort of the global perspective. While the city solutions have to be hyper-localized because each city is different, the demographics are different, the pain points are different, sort of the funding structure may be different. Ultimately, it is our responsibility to find common themes in this global opportunity. And that's important because it's when we find common themes that we will find scale. And when we find scale, we are able to reduce the cost. We are able to make these things economically feasible and ultimately unlock this virtuous cycle of demand creation that leads to cost reduction, which leads to more demand creation. Because otherwise, these massive investments we are making as an ecosystem in emerging technologies like AI and computer vision and 5G won't make sense. But if we find that global scale, suddenly from an economics perspective, this makes sense. So the first trend I want to talk about is this notion of edge computing. And very simply put, edge computing is all about putting compute, storage, and the ability to analyze data close to wherever the event is happening, whether it's a camera looking for a parking spot or detecting a pedestrian crossing the street, or any other safety issue that might be happening in a city context. So this is important because of a few reasons. First of all, if you look at a few years ago, there was the simple notion that we'll have a lot of sensors at the edge and all the intelligence and the ability to analyze will sit in the cloud. Well, that's completely changing. And it's changing because of a few key drivers that I'll get into in a minute. But think about things like optimizing the total cost of ownership, complying with the data ownership requirements for a particular city or a country, and also requirements around latency. And we'll get a bit deeper into this. But this notion of edge computing and this notion of real-time analytics at the edge is an ongoing trend that is only going to accelerate as we go forward. And we'll show you how we've adopted this sort of secular trend within the technology vector into the City IQ platform. But before we do that, we have another poll question for you. And the question is around sensors with edge computing. So have you a use case where you're deploying edge computing, where AI and machine learning are done on the sensor device itself, whether it's the learning part or the inference part? And if yes, what are the use cases for the sensor data or the device? We would love to learn more about it from our audience. So I'm going to pause for about a minute and give you the opportunity to select amongst things like traffic optimization or parking management or pedestrian detection, bicycle detection, gunshot detection, noise detection, license plate recognition, facial recognition, and I'm sure there are use cases that we have not listed or we may not even be aware of because we're discovering new use cases every day. that you're applying AI and machine learning at the edge for. So let me pause here. Okay, as Austin mentioned earlier, we'll compile the data and share with you post this webinar. So coming back to the notion of edge compute, let me quickly summarize some of the things everybody on this call should be thinking about as you think about deploying solutions. Think about real-time analytics, compute at the edge for reasons of latency. Think about a traffic light that should change because they've detected a pedestrian for their safety. Or in the future, think about autonomous cars or drones that need to have low latency real-time control. There is a cost to moving all the data to the cloud. Watching 24 hours of cars go by is not very interesting. Detecting an accident or detecting a situation where there is a traffic jam, these are event-triggered intelligent insights that we are interested in. And so that's the subset of the data that's relevant that you would like to either analyze or move back to the cloud. From a data privacy and data sovereignty, this is a very important aspect. I travel in my job, I travel and talk to cities in every part of the world. I was in China last week. I'm in Copenhagen this week talking to the largest transportation solution providers globally. And it's very clear that starting with GDPR in Europe and some of the new things that are being adopted in the US, data privacy and data sovereignty is going to become an increasingly complex topic. And so we have to think about what can we do with data at the edge without having to send everything back to the cloud and storing it. In fact, I think this is public information. One of the deployments of City IQ is in the city of Portland, where they're able to do real-time metadata extraction right at the edge and delete the video footage and only keep those intelligent insights-based data sets. The data that's captured and analyzed at the edge will obviously have more context. That context may or may not be available by the time the data is consolidated in the backend server. There are many scenarios where you cannot expect to always have connectivity, or the connectivity may be limited or expensive. So for all of these reasons, it's imperative that we start thinking about real-time edge computing. To give you some sense of the amount of data we are talking about, the average internet user creates about 1 gigabytes of data. We expect about 1.5 gigabytes by 2020. Autonomous vehicle will bring this up to about 4 terabytes. An airplane is about 5 terabytes. By the time you get to an autonomous or semi-autonomous factory, you're talking about 1 petabyte. But if I take all of these and I aggregate them at the city level, you're talking about zettabytes of data. And I'm sure some of you will now start Googling for what a zettabytes is. So let me make your life easier. It's 10 raised to the power 21 bytes. This level of data, this amount of data, we have never encountered before. And there is no traditional computation technique that can help us munch through and make sense of this level of data and give us insights. And so that's why the notion of AI becomes even more imperative. So when you're thinking about artificial intelligence, there's a lot of media conversation around future users, its impact on jobs. For me, it's much more near-term and much more real because AI will transform virtually every industry. All this data that you're analyzing at the edge can be utilized to make those edge devices more autonomous, more aware, more intelligent. And this impact will be felt across all the industries. But for the purpose of this conversation, think about governments and how they engage with the constituents. Think about the energy efficiencies and how utilities manage their networks. Think about transportation, which consistently comes up as one of the top 2 use cases in cities, the other being public safety, and how the notion of artificial intelligence will start helping. And we don't have to wait for that perfectly autonomous world. Things are happening today that are helping reduce traffic congestion, helping find parking more easily, helping reduce air quality pollution because of lesser vehicles going around in the city trying to find parking, and on and on. It's important to understand that this notion of AI, today there's a lot of conversation about AI in the data center, and that growth will continue. But increasingly, the artificial intelligence will be a distributed notion. Everything from things at the edge to the edge compute we talked about, to things like network infrastructure. How do you optimize the bandwidth end to end? And finally, how do you optimize both the learning, the training piece, as well as the inference piece at the edge and in the cloud will become more important. I want to quickly show you the data analytics journey and why AI is becoming more important. So as you read the complex chart that's in front of you, we go from the bottom, which is today, to top, which is more and more cutting-edge emerging technologies. The initial application of AI was frankly hindsight, which was basically telling us, describe to me what just happened. We got video footage, we took it back to the cloud, we analyzed it using AI and detected there was an accident. Great, okay. But the accident has already happened. We can't do much about it except maybe learn going forward how to prevent it. The next stage was diagnostics. Why did this accident happen? Was it because of congestion? Was it because of a driver error? We were able to do those analytics. This stuff is available today, and it's helping make us operationally more efficient. But the next step is predictive analytics. In other words, if traffic is starting to build up in a certain part of the city, is it going to increase the likelihood of an accident or a pedestrian being hit? And can we predict it? We go one step further. If we can predict it, is there something we can do about it? Route the traffic, in this case, more intelligently, so we prevent those situations from happening. Or when we detect a pedestrian crossing the street, control the traffic lights to prevent that accident from happening. One of the top use cases we hear from cities is make our streets safer. And one of the metrics they're constantly asking about is, tell me about the near misses. I have data on what actually happened, because if there's an accident, there'll likely be a police report or somebody will report it. But what I have no idea about is near misses, because those near misses are a good predictor for actual accidents. And finally, as we continue this journey, the next stage you're going to see is not just tell me what to do about it, but can I learn? Can I mimic human thinking in terms of learning and applying this data analytics over time? In other words, everything I'm learning real time from all these events that are happening, can it help me design a transportation system from ground up that's safer, more efficient, has a lower cost of operation? And so this is a fascinating journey, but as you do this journey, there are quite a few options on the table around how we implement the artificial intelligence. And in the interest of time, I won't spend too much time going into great detail, but think about cognitive reasoning, think about machine learning, and think about deep learning as three different approaches to AI. All of them have their own pros and cons, and I'm going to get a bit deeper into differentiating between machine learning and deep learning because these are very frequently used interchangeably. Sorry, just 1 second here. Okay, so let's start with machine learning. The notion of machine learning is very simple. So the system that's sitting in the GE City IQ platform, you can tell it that, hey, I need you to look for a bicycle. And by the way, a bicycle typically will have two wheels. It'll have a frame that looks sort of triangular in shape. You will likely see a seat and a handlebar. And you tell it about the features, and then you expect some level of analysis to say, have I detected a bicycle crossing the street or not? The challenge here is the intelligence of the system is limited to what features you've informed it about. And so if the bicycle is now at a different angle, or that bicycle has some unique features that were not in the standard description that you gave it, the system will not be able to detect it. So the second approach that we take is the notion of deep learning, wherein in this particular case, you would feed the system tons of different kinds of images of bicycles. And you allow the system to learn what a bicycle looks like, pretty much like how we as humans learn about what a bicycle looks like. And that learning is captured in multiple levels of neural network. And once this learning process is done, then the system is capable of recognizing a bicycle, even if it doesn't fit some of the restrictive feature description that we talked about. So in other words, now the system is able to detect on its own what are the right features it should learn about a bicycle. Once it's done that, the next stage is, okay, we trained the system pretty much like we train a human brain, or we all got trained, we grew up as kids, we learned what a bicycle looks like, and now every time we see a bicycle, our brain tells us, yes, this is a bicycle. How does the system do this? The system does this by doing a couple of things. The first part is, in the training process, you have to tell it positive and negative use cases. So what we're showing on the slide here is, you're going to tell it what a bicycle looks like, but you're also going to tell it some other things like humans or strawberries that don't look like a bicycle. So it's able to differentiate both the positive and the negative matches. And so once that training has happened, every time the system sees a bicycle, it's able to detect. Now, there are a couple of very important things that we need to learn about how the system needs to be designed. First of all, the deeper the neural network, the more intelligent both your training and inferences. So the more compute you have at the edge, the more efficient your artificial intelligence will be. And the second thing to keep in mind is the more the data that you can feed into the system, the more intelligent it will become. And again, I go back to the human analogy. If all I've seen is one bicycle in my lifetime, I will likely be able to detect that bicycle. But bicycles of different shapes and sizes, that intelligence would not yet be ingrained into my brain. So data sets are extremely important for training. So where does this bring us in terms of where things are today? Earlier on, you heard Austin talk about a lot of our consumer devices and experiences that have started to feel very intuitive. And I want to give you some background on why now. Why does it feel so intuitive in the more recent past? So on the slide, you can see two graphs. The way to read these graphs is on the y-axis, we have the error. So lower is better. And on the x-axis, we have the passage of time. So what you can see is the graphs are sloping to the right and towards the bottom. What that means is over time, the error the machines are facing in whether it's image recognition or things like audio analytics, it's going down, which is good news. But then you look at the red dotted line. It's only in the recent past that these systems have become capable or even better than human capability to detect images and sounds, which is pretty phenomenal. And so that's why these experiences have started becoming more intuitive. But what I'm even more excited about is the ability for systems like GE City IQ now to mimic human behavior and that level of intelligence. So let me bring it all back. We talked about edge computing, we talked about AI, we talked about data analytics. GE City IQ is a system that was conceived right from the start to have the capability not just for machine learning, but also deep learning. In other words, it's constantly learning and becoming better over time. It's not a fixed functionality device. And when I say better, it is along two vectors. It's going to become better at whatever it does today. So if a pedestrian detection is the primary use case for the city, it's going to do it better over time as we do over-the-air updates and give it better algorithms. But equally importantly, it is also capable of adding new use cases, because when we design the system, we plan for some level of headroom. So today it's about pedestrian detection, and I'll share a real example. Austin and I were talking to a certain city, and they said, well, this is great, but I have a use case around strollers or kids crossing a pedestrian intersection. Can you tell me that? And the simple answer is yes. With some amount of code development, we can develop that particular use case, because we have the compute and we have the headroom and we have the underlying artificial intelligence capability to enable these new use cases. Let me show you how the system became better over time. So we're going to go through a couple of video clips. The first video clip, which should be playing right about now, will show you the initial implementation that was based on machine learning. So back to the example I shared about how a bicycle is identified using its features. So you can see in this example that we are able to detect multiple kinds of vehicles as they go past the street. And that's a great capability. But once this clip finishes, I'm going to show you the capability of the enhancements that happen once you bring in deep learning as a next stage. So we'll give it a few more seconds. Okay. So now we go to the next clip. And what you will see in this clip, again, going back to my description of deep learning versus machine learning, now the system can actually learn that there are not only cars and vehicles going by, there are bicyclists and there are pedestrians that are walking by. And the system is able to learn and differentiate among them all by itself. And again, this mimics the human capability, the human behavior to see more. I don't know if that clip played or not, but hopefully you guys saw the ability for the system to detect and differentiate between those three different classes of objects. So we started this by talking about the product, and I talked about a few things that we have in mind, both in terms of the current product, but also the future evolution, working with GE and AT&T. This system is actually being actively deployed across the United States as we speak. San Diego, which has been by far the largest deployment, Atlanta and Portland are the notable ones, but you can see the deployments in San Diego and San Jose, Dallas, Farmers Branch, and Schenectady, where some of the earlier deployments were done. So we are starting to see a pull for this product, and we are also starting to see an ecosystem starting to develop around the data platform that Austin was referring to earlier. I want to touch on one other quick thing before I turn it back to the organizing team. This entire system is developed on is based on the Intel OpenVINO toolkit. And OpenVINO toolkit, very simply, is a set of APIs. It's a software stack and a software development environment that allows you to put vision-based capabilities and AI at the edge, AI inference at the edge across different applications. We understand that there is no one fixed architecture for artificial intelligence. Some people would like to use CPUs, others would like GPUs, others would like VPUs, visual processing units, or you may use an FPGA accelerator. What OpenVINO does is it takes all the
So I think we might have lost Sameer. I'm going to keep going on his behalf. Sorry about that. I know Sameer is traveling, so he might be in an area that is a little bit more remote. So basically, the OpenVINO toolkit, if we go back to that slide, just to hit on that quickly, is a very powerful access network to the deep learning tools that come from the edge device. So when you think about all of the capabilities and all the possibilities that you could possibly program on the Intel Silicon using their deep learning software stack, it becomes very intriguing to the development community as to certain things that they might want to build themselves. Let's just pretend that you're in a Midwest city and you want to detect potholes on the ground. Maybe you write a piece of software on the OpenVINO toolkit that helps the city's sensors detect where open potholes are. It's things like that that could be very, very powerful in making sure that not only are the needs met of the citizens today, but that as use cases shift and as priorities shift in the city, or as the utility is serving the city, as those priorities change with population changing and the environment changing and everything else, that you have a very flexible system. So not only can you build apps now from the cloud, but now you can go down to the edge and build out the sensor capabilities that you want. So it's an extremely powerful toolkit, and it's open to the OpenVINO developers.
Thank you, Austin. This is Sameer. I'm back. I was trying to give an example of limited or sporadic connectivity. Unfortunately, my connection dropped. I'm back on the call. Austin, would you like me to take over and continue?
All you, Sameer. Welcome back.
Right. Thank you. Thank you. So when I unfortunately dropped off, the OpenVINO toolkit actually enables all the well-known frameworks already optimized. And if you're a software developer, an application developer, it preserves your investments irrespective of the underlying architecture, because the APIs that you're programming to stay consistent. We already have seen strong interest from the ecosystem, and the City IQ solution was one of the early adopters of this very capable toolkit. Since we lost some time, I'm going to skip over a couple of slides. When we look at the artificial intelligence investments, I just want to emphasize that it's not just about the hardware architecture, it's about an ecosystem. So we as Intel and with our partners like GE Current, we are investing at platform level, at the tools level, optimizing the frameworks like Café that are absolutely critical. We are releasing open source libraries as well. And then in either organically or through acquisitions, we are building out all the technology pieces so that depending on your unique AI inference at the edge requirements, you have the ability to choose a CPU, integrated graphics, a discrete GPU, a VPU, or an FPGA kind of an accelerator. And in future, there may be new kind of hardware architectures that will come along. But from a software development perspective, we want to make sure the investments you're making are preserved and give you more value over time. With that, I want to turn it back to Austin and talk a bit more about some of the tangible use cases and the impact we are seeing with the City IQ solution. So Austin, back over to you.
Thanks, Sameer. So what we've heard now is a pretty comprehensive overview of, why cities need data, what kind of data would be interesting. Sameer gave you some great examples of how we're going to utilize that data in the future with this platform. And we thought that it would be helpful for our audience to just talk about some of the things that we're doing today and some of the things that we're working on for early next year. And what it really comes down to is, as I go through this list, it's a little bit cliche to say it, but you can't manage what you can't measure, right? And so what we're enabling is a significant amount of measurement in the city that can then lead to an outcome. The first example here is probably one of my favorites, because when you think about the early example of how the computer vision was detecting a car entering and exiting a parking space, those two events, the park in and the park out event, going to the cloud and landing in an application through an API can be used for a number of different use cases. But one that we have found to be significantly beneficial is guiding consumers to an open parking space. So imagine you want to go downtown or to the other side of town to your favorite restaurant, and what's the first thing you do when you get there? You're looking for a parking space, right? You're probably circling the block, trying to figure out, well, should we exit here, exit there? If you had an app on your phone that could tell you exactly where all the on-street parking spaces were, not only would that deliver a service to you, because now you can get to where you want more efficiently and faster, but it also has an impact on the rest of the citizens, because now everybody knows where the parking spaces are. And what we've seen through studies and some of the impacts from our ecosystem partners that have deployed this is a reduction of up to 30% in congestion just by notifying citizens where the open parking spaces are. Another example we gave you was car counting. And one thing that we've learned is a lot of cities don't really have a lot of reliable data around traffic. They don't have ubiquitous coverage of traffic counts. And so what we're able to do with this car data is take it and put it into what we call a digital twin, or a model that emulates how the city changes with various traffic conditions. And when you build that type of model and you can simulate something that's extremely realistic, like almost to the exact mirror of what's happening in real time, you can come up with some very interesting design ideas for how to improve the streets. You can even do dynamic traffic signal changes. You can start offering citizens in certain areas, more promotional ideas around how to leverage public transportation, bicycle mobility. A lot of things can happen when you finally understand at the core what is happening with my traffic movement. Similar with pedestrian movement, right? Sameer mentioned a great use case about near misses. And so when you think about where are pedestrians and where are cars, and how do those two intersect or almost literally intersect or overlap each other, you can get a very foundational piece of data around where your high risk areas are. Traffic speed, right? Just knowing not how many cars are passing by each sensor, but how fast is each car passing by each sensor can give you an extremely powerful ability to dynamically change your streetlights from red to yellow to green based on the actual demand of the system at hand. So while cities are most cities are sophisticated in using timers based on known congestion, what's not taken into consideration is what if something changes? What if there's a car accident? What if there's construction? What if there's something that changes that area, in which case then a whole new timing study would have to be done. In this case, you have it all dynamically integrated, so it does it automatically. Vehicle type by location, right? Imagine being able to count, car versus truck versus van and feeding that into the digital twin model I mentioned earlier. Now you can start understanding origin destination of these vehicles and really start to think about how you optimize some of those routes based on how the city is changing. Bicycle counting is very similar to this, but again, you can't manage what you can't measure. So how do we increase mobility and plan around an increase in bicyclists and safe bicycle paths if we don't know where they are, how fast they're traveling, which direction they travel, what time of day? So getting that data in can help significantly increase the utilization of bicycles through just simple planning and other application tools that can help enhance the actual safety of the bicycle usage. When we talked about shopping carts earlier, there might have been an unspoken message here, but one of the things that we're learning from a lot of our city customers is that the homeless population is beginning to migrate in various areas of cities, and they're having a hard time tracking where they are, where they go, if they need assistance. And so just being able to identify, through a simple count of how many shopping carts are where, it can give us a very strong indicator of these patterns and can help enable us to try and help those in need a little bit more effectively. And similar with wheelchair access, right? There's with the increase of mobility and trying to encourage more usage of transportation outside of your own personal vehicle, how can we make sure that we're improving accessibility for everybody to make sure that as they want to get around the city, they've got a safe and efficient way to do that? So these are some of the real things we're doing today with our city customers, And all of these are enabled by the computer vision technology that's provided to us by Intel. With that, we have another question for you. So if you wouldn't mind taking the next 45 seconds or so to answer, what is the #1 outcome you are driving for your city? Obviously, if you're a city official, you can answer that question more directly. If you're a utility, think about the cities that you serve and which of these might be most impactful to your area if you were to be able to provide this as a service to your cities. And for those of you that are not a utility or a city, just answer in terms of what would you prefer to see in the city that you live in or work in most often. And since we're only down to 5 minutes, I'm going to turn it over to Jim now for Q&A.
Great. Thank you, Austin and Sameer. We got a lot of positive comments throughout the webinar. Now let's open it up to a few questions. The first one, I'll turn to you, Austin. So there was a lot of questions about personal privacy. With video cameras now in our city spaces, how do we go about protecting personal privacy?
That's a fantastic question. So I think the most important thing to think about when it comes to this technology is the fact that we are using optical sensors, which are certainly a form of camera. They are not actually bringing in the camera feeds for what's going on outside. So what they do is, when you saw those examples of the videos, they are identifying the object of interest, let's say a pedestrian or a bicyclist or a car, and then it's extracting just the metadata from that particular event and bringing that data to the cloud. So I don't know who is walking in the crosswalk, who's running, who's parked, right? All I know is that a person is running and a car is parked. So it's just the metadata. The second thing I would say is that when it comes to anonymizing all of the data, we use an additional step of privacy filtering with the optical sensors. So we're only going to be extracting data from sidewalks and streets. Anything above, let's call it ground level, will essentially get filtered out. So there's no questions about whether we're, counting the number of people on a second floor of a building or something like that, right? It's always going to be what is on the streets and the sidewalks that is in the public domain and is accessible by everyone and is basically, assumed that the government and the cities are helping make those areas more efficient and safe.
Okay, thank you, Austin. Sameer, I'm going to throw this one over to you, and I know we only have a couple minutes left, and you could probably talk on this topic for hours, but with the enormous amount of data that's going to become available, how do we, protect that in cybersecurity terms from falling into the wrong?
Jim, I think we lost you for a second. Let me just play that back. The question was around the large volume of data and protecting it from a cybersecurity perspective. Did I get that right?
That sounds right, Sameer.
Okay, thank you, Austin. So folks, that is absolutely one of the things we have to think about when we design the end-to-end solution. So I think part of it is addressed by the fact that a lot of the data that's collected is actually anonymized, and the metadata from that is extracted. But thinking about the data housing, where is it housed? Is it encrypted or not encrypted? Who has access to it? The data access policy. These are all part of a comprehensive data security review that you must do, that everybody adopting these solutions must do, and I believe most people are doing, to make sure this data, even the metadata, is not compromised in any manner. When we get into the debate around security and privacy, one example that I use to illustrate the point is, we can close all the windows and the doors in our home to prevent, once in a while, thunderstorm from coming in. But when you do that every day, you're also preventing fresh air and sunshine from coming in. So I think we all have to find the right balance of data access and data security. And there is no one-size-fits-all answer to this. Depending on the regulatory policies, the legal rules, the cultural nuances of which city, which part of the world you're talking about, there will be a different balance that will need to be achieved. It's an ongoing topic of discussion. It's a very valid concern. And I think increasing awareness around it and sharing best practices across the ecosystem, those are two of the things that we should be able to do, we should be doing today to solve this issue.
Thank you very much,
Back to you, Jim,
Sameer.
if you're still there. Oh, thank you.
Fine. So, Austin, Sameer, I want to thank you. I want to be cognizant of time, everyone who's on the line today. If we weren't able to get to your question, free to email me, and I'll try and answer all the questions I can at james.benson@ge.com. Also, we'll post a recording of this webinar, so feel free to share it with others who you think could find it valuable. And in closing, I want to thank Austin and Sameer, and I want to thank all of you who joined us today for the webinar, Building Blocks for an Extensible City. On behalf of Current by GE and Intel, thank you again, and have a great rest of your day.